This problem is the first one that involves, as we said here, two quantities, or more than two quantities, right? If you write a formula for how it's related, you are looking at the volume of this thing. Now, in here, this says 4 centimeters and 2 centimeters, but it's the same problem as actually this, which is this thing is representing a swimming pool in my backyard that's the shape of a cylinder. Okay, a few years ago we bought one of these, or my mom bought it for my kids. One of those big cylindrical swimming pools, and so I decided, okay, it was about 3 or 4 in the afternoon or something like that, and my kids were saying, "Oh, can we fill it up? Come on, can we fill it up?" And I said, well, besides the fact that even if you fill it up, it's going to be freezing right now because you have to wait for it to warm up. But sure, let's start filling it up. And I'm curious of how fast it's going to fill up, right? So that's what this thing is related to if we change those numbers. I waited for 4 or 5 hours, and probably that's how much I had in it, right? About that much. Then the question was, it's taking so long to fill up, do I leave the hose on overnight or not, right? Because if it gets really full here, there is always the potential that it gets so full it starts running over the side, and then maybe the whole thing collapses over and I flood my neighbor's house because it's a bit lower than mine. All this big tidal wave goes through the person's bedroom because they sleep at the back of the house anyway. So it's not my house. Oh yeah. So if I flood their house, it doesn't matter, right? So anyways, I'm worried about these kind of things, right? Now, really, you don't necessarily need to do calculus because you can kind of do this average rate of change here, right? Because it is, I'm filling it up at a constant rate. How could I measure that? That's something easy to measure, right? There's 2 rates involved here. At what rate does the surface of the water rise? And there's this one. This one is given in the problem. This one's not given. The reason is because this one's a lot easier to measure in real life. How, and I'm not just saying I did this, I actually did this. How do you measure how fast it's filling up? So do you sit there and watch the surface rise? Like, it goes up so imperceptibly slow. It's not quite like watching the grass grow, but it's this is going up like this, right? But it's not going nearly this fast. You can't see it going up, right? It's going so slow. It's going to be hard to try and count how fast the water's rising without sitting there for a couple hours, right? This is a lot easier to measure, right? How could you measure that? This is the water's being poured in at that rate. How can I measure how fast water's being poured in? There's a hose in the thing, right? How can you measure that? Think about it. Well, it's not the velocity. It's not centimeters per second. It's centimeters cubed per second. What is this a measure of? Volume, right? How can you measure how much volume is? Imagine the hose is here, right? There's a hose, which I guess we can make green, just the same color as the grass, and we'll make it brown. I don't know. This is not going to help seeing it, but here's the side of the house. Hose goes, I think it either connects to something there or whatever, but it's filling up that. Actually, no, it's not. It goes over the top like that. But so it's filling this up. How can I measure? Here's the water coming out. Water's coming out like that. How can I measure how fast it's coming out? Get a bucket. Thank you very much. Get a bucket. Here's a bucket over here. This happens to be a, 10 or 20 liter bucket or something like that. Now you have to start to think how many cubic centimeters are in a liter and stuff like that. But I think you can understand. If you have a bucket over the side and it's 20 liters or 10 liters or whatever, you can see how long it takes to fill up the bucket. You know the volume of the bucket, right? 20 liters, how many cubic centimeters, 20 liters? 20. How many cubic centimeters in a liter? Those little cubes, cubic centimeters. A liter is like a block that's 10 by 10 by 10. There's 1,000, right? A milliliter is a cubic centimeter. 20 liters is 20,000 milliliters, right? Or 20,000 cubic centimeters. Anyway, so you have this thing, it's that much. You measure how long it takes to fill that up. So then you say that divided by however long it takes, 10 seconds or something like that. What would I get? What would my rate be? 2,000 cubic centimeters per second. So you can get that rate easily, right? It only takes me 10 seconds to measure that. It would take me hours to measure how fast it's actually going up the side of the thing. Okay. So anyways, you do that, and you don't necessarily need calculus for this because the rates are, because if it's pouring in at a constant rate, then the water's going up at a constant rate. Okay? But because all you need to do is then say, well, the total volume is, you'd have to work out the whole volume and figure out how many of those buckets it would take to fill it up and do that. But you can write a formula for this pretty easily, okay? And you can use calculus to do that. If you know the volume of a cylinder, right? So this is a cylinder from the side, right? The circular base is not changing, but it's the area of the base times the height. That's the volume. When you write the formula for this, you've got dV dt. You got the derivative of this, but which thing did we say was the variable there? This is the variable. This is constant. The pool is not getting wider, right? And when we talk about the cylinder, are we talking about the entire pool? We're only talking about the cylinder of water, right? When we talk about the cylinder, you have to call this, the height is changing, right? Really, I should be showing the height as down here, right? This should be like this, right? And then when the water is going up, we should think about it as, it's like a cylinder where the height is changing, right? Height's going up here. I didn't draw it exactly in the right place there, but the height is going up. Now the water is obviously going off the bottom of the pool too, but anyways, height is going up along with the water rising. This is a variable, this is fixed. If you find the derivative of this, so if you say the derivative of all of this stuff, pi r squared h, just put all of this outside because it's constant. Remember we said you got to look at variables and constant. We really have to understand what we mean by variable. It's not just a letter, or it's not just a bunch of letters. It's something that is changing in the situation. The radius is not changing, so it's a constant. So it can go out here. Okay? We're gonna continue working on that next